Alright, so this is another great example and something that I often do in actually my own research work. What we have here is the single degree of freedom and free response. And we're told that the system is governed by the single degree of freedom system mx double dot plus cx dot plus k dot equals f of t. And we're looking at the free response here, obviously, not the forced response, so f of t would be 0. And we're told that we've measured the mass of the system already, and we're asked to find the damping coefficient from this free response plot. So the first thing I want to note here is that we know that c divided by m is going to equal 2 times zeta times the natural frequency. And this is important for us because what I can basically extract from the graph is some information about both omega n and also about zeta. And here's how I'm going to do that. I'm going to start, and I'm going to use a technique known as logarithmic decrement. And log dec basically says that if you can estimate the amplitude of two consecutive peaks, that you can get essentially an approximation for the damping ratio zeta. So in this regard, probably what I would do is I would come in here and I would pull off two peaks, and so we could pick off this value here. And what I would typically do is say that something like x1, and I'll use that to denote the first peak, is given by approximately 1.4. And if I come here and pull off the second peak right here, that x2 is probably approximately given by, oh, this looks to be about 0.75. And if I wanted to do one more approximation, say I can get x3 is about equal to, oh, maybe something like 0.4. Now you only need two of these to pull off the measurement. I typically do a couple of them just to check. There's also an approximation where you can do this over multiple periods, but I believe the single one is emphasized in the notes. And what we can basically do here is we can say that the logarithmic decrement, which is typically denoted as delta, will be the natural log of the ratio of two consecutive peaks. So we can call this, for example, x1 over x2. And that will equal 2 pi times zeta divided by the square root of 1 minus zeta squared. Now that's something you could solve numerically if you'd like, using x1 and x2 to get zeta. Of course, you could also write the same thing and write that the logarithmic decrement of x2 over x3 is also equal to 2 pi zeta divided by the square root of 1 minus zeta squared. And you could get another estimate from zeta for this. Okay, the other thing you can do, and this is probably not too bad of an approximation here, I'm not going to punch the numbers for you, but you're welcome to do so, is you can note that if zeta is small enough, you can approximate this even one step further and say actually that zeta is simply equal to 1 over 2 pi times the natural log of x1 over x2. And this gives you a nice numerical result typically as well. Now once you have that, if we go back to our expression up here, we know from here that C is going to equal 2 times m times zeta times omega n. This of course means that we now have m, we now have zeta, but we still don't know the natural frequency. The way I do that is I typically try to estimate it, roughly speaking, from the graph. I know that if I measure the change in time between two consecutive peaks, this gives me one period of the response, and this is going to be t sub d. I know the period t sub d is equal to 2 pi divided by the damped natural frequency omega d, which is 2 pi divided by the square root of 1 minus zeta squared times omega n. If I've already determined zeta using the logarithmic decrement method, I can get an estimation of omega n from here. Once I do that, I now have all of the quantities on the right-hand side for my expression for C, so you can do a little bit of numerics here and get the answer you seek. I encourage you to go ahead and work through this. Maybe try a couple different peaks in the logarithmic decrement and use a couple different increments to estimate the period. What you'll find is that you can get a fairly good approximation for each of these quantities. In the real world, if you were to go out and do simple free vibrations testing, this is the type of experiment that people actually do. We do it all in the time in my own research group as we look at things like micro and nano resonators. Very small scale systems that you can't pick up, weigh, etc. But you can typically always do a logarithmic decrement measurement, and that's what makes this pretty powerful. Take care, everybody.